Good morning. My name is Julio from the University of São Paulo. The title of this presentation is Continuous Versions of Haack Puzzles: Equilibrium, Steady, or Eigen-states, and Ontologies. For a long time, the philosopher Susan Haack has been working with the crossword metaphor, in which she compares the scientific activity, the activity of formulating scientific theories, with the activity of solving a crossword puzzle. My goal is to extend this metaphor by taking some limits of a crossword puzzle. A crossword puzzle is a discrete puzzle. I will try to examine some puzzles in the continuum. In this extended metaphor, solving a continuous puzzle is to find some states that we call equilibrium states or steady states or eigenstates of the continuous system. I will analyze some essential properties of these solutions. We will see that these solutions can be characterized as precise, stable, and composable. Finally, I will relate these eigensolutions, these solutions in continuous puzzles, with basic entities of a theory, with the entities that belong in that theory ontology. This slide has three illustrative figures. The central figure is a postal stamp celebrating 100 years of crossword puzzles. The stamps at the left and at the right celebrate Ohm's formula and Kirchhoff laws. Put together, those two statements describe an electrical circuit as a linear system. Linear systems describe the simplest theories in the continuum that can be found in science. For this reason, we will use several linear theories to illustrate our ideas. This presentation is structured as follows. On section 2, we discuss Haack's fundamentism and crosswords, discussing the essential properties of good solutions for discrete puzzles. On section 3, we discuss invariant states and equilibria in linear systems. We also discuss some essential properties of these states, namely stability, precision, separation, and composition. At section 4, we discuss chemical affinity tables as analytical puzzles. We present the historical evolution of these tables from discrete inequalities to continuous equilibria, from static to dynamic invariants. At section 5, we discuss invariant states in dynamical systems and the all-important concept of eigensolution. At section 6, we come back to the concept of words. We discuss production cycles, ontologies, and symbol grounding. At section 7, we present our final remarks. The basic question of epistemology is how can we know or how can we prove that an hypothesis or an hypothesis in a theory is true. Munchausen trilemma, also known as Agrippa-Deceptic trilemma, states that there are only three ways of proving a statement. The first way is by finite regress or finite deduction from foundational statements. Those are unquestionable statements, ideas, axioms, empirical facts, observations that we take for granted. The second way is by infinite regress. I know something because my daddy knows it, because my grandfather knows it, and so on. That's very hard to use in empirical science. The third way is circular argumentation. Of course, it is easy to use circular argumentation to make funny arguments. I'm innocent because my accomplice in a crime swears that I'm innocent, and vice versa. However, circular argumentation in complex theories can be used to check the theory general coherence, and that is something very important. The philosopher Susan Haack denounces the exclusive disjunction of the trilemma. She says that both finite regress and testing the coherence of a theory are both important in the process of proving or corroborating an hypothesis. This combination she calls fundarentism. In order to advance the case for fundarentism, Susan Haack uses the crossword puzzle metaphor. How reasonable a crossword entry is depends on how well it is supported by its clue and any already completed intersecting entries. How reasonable those other entries are, independent of the entry in question, and how much of the crossword has been completed. How warranted an empirical claim is depends, analogously, on how well it is supported by experience and background beliefs. How warranted those background beliefs are, independent of the claim in question, and how much of the relevant evidence the evidence includes. The natural sciences, at least, have come up with deep, broad, and explanatory theories which are well anchored in experience and interlock surprisingly with each other. And as plausibly filling in long, much intersected entries in a crossword puzzle greatly improve one's prospects of completing more of the puzzle, these successes have enabled further successes. I believe that fundarentism is a great idea. Nevertheless, some topics deserve further analysis. First, we should clarify what's the positive role of circular argumentation in construing, proving, or corroborating a scientific theory, other than, of course, taking coherence as a trivial necessary condition. Next, we should ask the following questions. What is the most appropriate form to present a scientific hypothesis H in the scope of a statistical model or logical formalism? Then we can ask how exactly to build and interpret a measure for the value of evidence in support of hypothesis H given the observational data X. I will now present some ideas on how to answer question number 1, also hoping these ideas can pave the way to answer questions 2 and 3. Atkinson and Pijnenburg have tried to answer question number 1 considering very large theories or very large crosswords. If a scientific theory is similar to a crossword puzzle, then a theory of everything, a theory that explains everything in the universe, is analogous to a huge crossword. Moreover, Atkinson and Pijnenburg argue as follows. As the complexity of the crossword increases, the ambiguity in general decreases. It becomes more and more difficult to come up with different solutions. The number of coherent ways of filling in a finite crossword with a finite alphabet, irrespective of lexical constraints, is finite. In the end, if the crossword puzzle is sufficiently complicated, there might be only one solution. It seems to me that's a very powerful argument explaining how we can use coherence arguments to access, at least in part, the truthfulness of an hypothesis or a theory. Nevertheless, I would like to have similar arguments that could be used for small theories, small models, like those found in ordinary empirical science. I want an operational notion of truth for theories of limited scope, but capable of very high precision, like Newtonian physics, Lavoisier chemistry, or Ohm and Kirchhoff circuit theory. I will now start a small digression studying some of the characteristics of the best crossword puzzles. I will analyze the crossword that is considered by the community the best one ever made. That's the crossword published by the New York Times on November the 5th, 1996, one day before the presidential elections. The solution to this crossword has 3 words of maximum length running all the way across the grid of size 15. Near the top and the bottom, we have the words prognostication and Mr. President. At the center, we have a solution entry that can be either Clinton elected or Bob Dole elected. Of course, Bill Clinton and Bob Dole were the Democrat and Republican candidates on that election. Whatever alternative is chosen, there are corresponding vertical entries that match the vertical clues. The first thing to notice about this crossword that the specialized community thinks is the most amazing one ever made is that it is a game of standard size, 15 by 15 letters. This puzzle also complies with the standard composition rules of crossword games. Each separate word has a correct spelling and meaning defined by a standard dictionary. Of course, letter coincidence is also required wherever words join at grid intersections. As we had already mentioned, we have 3 words of maximum length with 15 letters. These special words play very important roles in the game. First, these special words make very tight fits. The probability of a misfit is very low. Let F be the frequency of the letter that appears most often in the English language, and S be the size of the grid, in this case 15 letters. Then the probability of a random misfit of such a special word can be approximately bounded above by f to the power s. That makes the probability of such a random misfit of the order of 10 to the minus 13, approximately of the same order of magnitude of the relative uncertainty of the best known physical constants. Finally, those special words of maximum length can be thought as long bolts that hold the entire puzzle together, giving great stability to the game. This most amazing puzzle also uses the standard grammar and semantics of the English language to combine those special words with an extra level of meaning. Prognostication, Clinton elected, or prognostication, Bob Dole elected Mr. President. The 2 alternatives generate genuine solutions to this most amazing game. That is perhaps the most interesting feature of this crossword. There are several genuine solutions to the game. Moreover, the set of genuine solutions spans all pertinent possibilities. Using mathematical jargon, we would say that this set forms a basis for the outcomes of the presidential election. In physics and mathematics, we find systems exhibiting solutions with similar characteristics to the solutions that we have just studied. We call these solutions eigen-solutions. Let us now study some simple physical systems made up of weights, strings, and pulleys. The figure to the left shows a system with two masses and one pulley. This system has no stable equilibrium. The heaviest mass will fall all the way down. The second figure shows a system with three masses and two pulleys. As long as none of those weights is heavier than the other two combined, this system can find a state of stable equilibrium. The geometry of the system can be described by the angle made by each one of the strings joining at the central pivot with the horizontal axis. In order to find the equilibrium point, we decompose the three forces acting at the strings into their vertical and horizontal components. Furthermore, at equilibrium, both vertical and horizontal resultants must be zero. All these conditions are expressed by the linear system displayed in the slide. This system is characterized by forces of fixed magnitude, while the geometry will adapt to find the equilibrium point. Also noticed that the same geometry described by angles θ1 and θ2 that solved a system with masses μ1, μ2, and μ3 will also solve the system with masses alpha μ1, alpha μ2, alpha μ3. These scale invariants can be interpreted as a liberty to choose the unit used to measure masses or weights. The figures to the right show an analytical balance, an instrument that is conceptually very similar to the three-weight pulley system. This is a high-precision instrument, accurate to 5 parts per million. The simple fact that it's possible to build in practice instruments like this shows that the system is very stable. That is, the system's variable geometry will adapt to restore it to the equilibrium in case of any disturbance to the fixed forces μ. We will now study a second simple physical system that contrasts with the former one by having variable forces and a fixed geometry. This system has a triangular frame and three springs. One end of each spring can slide along a side of the triangle. The other end of the three springs are joined together at a free moving pivot. The position of the springs is represented by the segments ZA, ZB, and ZC at the figure at the left. The matrix S with fixed geometric coefficients is used to project the segments into the vertical and horizontal axis. The constant vectors R and K have the rest length and the elastic coefficient of each spring. Vector Z has the variable extension of each spring, and vector μ has the forces exerted by the springs that are proportional to their extensions. As in the previous system, at equilibrium, the resultant of horizontal and vertical decomposition of μ must be zero. The last equation is Viviani theorem, stating that the three components of Z add up to the triangle height. If this height h is 1, the components of Z can be interpreted as a fractional composition, and visual representations of Z, like above, are known as compositional diagrams or Definetti diagrams. It is easy to generalize either the spring system or compositional diagrams to higher dimensions, as suggested by the figure at the right. Compositional diagrams are routinely used in many areas of empirical science. For example, in chemistry, they can be used to indicate the molar fraction of reactants in a chemical system. We now come to the central section of this presentation, in which we are going to study the historical evolution of chemical affinity tables. Chemical affinity can be thought as the force holding together the parts of a chemical substance. In earlier times, a chemical reaction was conceived as a one-directional transformation, in which two or more chemical substances, the reactants, are decomposed and their parts are rearranged to form new chemical substances, the products of the reaction. In order to predict which chemical reactions are actually going to occur, we have to rank chemical substances by their chemical affinity. This situation is analogous to the physical system with one pulley and two masses. The heaviest weight, the stronger force, will determine in which direction the system will go. The figure to the left shows the affinity table published in 1718 by Etienne François Geoffroy, the first table of this kind, praised at the time as a system of axioms for the science of chemistry. We can think of this table as a discrete puzzle in which we have to rearrange the symbols corresponding to chemical substances in the correct order, an order corresponding to the rank of affinities. Conceived as a game, this exercise looks very much like solving the sliding puzzle depicted at the figure at the right. In 1786, Guyon de Morveau devised a far more sophisticated way to present an affinity table. Each chemical substance is conceived as the union of a base and an acid part. The integer numbers appearing in the affinity table convey the force holding the two parts together. The diagram below the table shows how to proceed to predict if a given reaction will or will not occur. The affinity numbers are arbitrary integer numbers in a given range, in this case between 1 and 70. The table is considered correct as long as all inequalities obtained in the reaction diagrams point to the substitution reaction that actually occurs. Hence, I say that such an affinity table looks like an inequality Sudoku puzzle. In this conceptual framework, reactions are always conceived as unidirectional, irreversible. However, people began to realize that when the inequality resulting from the reaction diagram was not very strong, the resulting reaction was very slow or even incomplete. Almost a century later, in 1879, Goodberg and Vaga presented a new framework for chemical reactions. In this framework, chemical reactions are not conceived as irreversible but as reversible, reaching a point of equilibrium. there is a close analogy between such a reaction network and the spring system studied in a previous slide. Instead of a matrix S of fixed geometric coefficients, we have a matrix S of fixed stoichiometric coefficients, giving the proportions in which the chemical substances combine. The vector Z gives the molar fractions of the different substances at the point of equilibrium. The affinity vector mu is interpreted as the force driving the formation of each chemical substance, that is a function of the molar fractions Z and a vector of thermodynamic constants. At this point, the metamorphosis of affinity tables is complete, from a purely discrete puzzle to a fixed point or equilibrium state in a continuous system. Reaction networks are dynamic systems in which chemical substances are constantly being decomposed and regenerated. Yet we speak of a steady state or equilibrium point. How can we speak of a dynamic equilibrium of an invariant form of movement? The figures at the slide show systems of two couplet oscillators, transverse oscillators at the top, longitudinal oscillators at the bottom. At the left, we see the static equilibrium state for these systems. To the right, we see dynamic invariant states or normal forms of movement for these systems. There are two normal modes of movement for the oscillating particles. A symmetric mode, where the particles move with the same amplitude and in the same phase, and an antisymmetric mode, where the particles move with the same amplitude but in opposite phase. Now, a fascinating composition-decomposition rule for this system. Any free movement of these systems is a linear superposition of their two normal modes, also known as systemic eigensolutions. Eigensolutions are also stable in the following sense. The energy stored at each normal mode remains constant. Finally, eigensolutions are precisely defined. The system symmetries impose strict invariant forms and precise oscillating factor frequencies, also known as eigenvalues. A similar system with n identical couplet oscillators will have n eigensolutions. We can take the limit of n going to infinity to model a continuous system. The pictures at the top display the vibrating string, the continuous limit of the transverse couplet oscillators. The eigensolutions for this system are exact trigonometric functions, and the corresponding eigenvalues multiples of the harmonic sequence, 1/2, 1/3, 1/4, and so on. The composition and decomposition rules for this system are natural extensions to the discrete versions seen in the previous slide. The abstract structure of these rules is known as a Hilbert space. The vibrating chord of a harp or a guitar is a very good approximation of such a system. Men and women have been using these abstract rules to make music long before they knew anything about Hilbert spaces. The NSF poster at the bottom right displays a couple of plain-tailed wrens. They sing a very complex love duet whose parts fit together like a jigsaw puzzle. Birds do what they do, but men can talk about the things they do. However, this talking requires the things they do to be named. The central figure at the bottom shows the standard names given in Western music for the notes and intervals used in the wren melody. We have now arrived to a key metaphor of the cognitive constructivism epistemological framework. Objects are tokens for eigensolutions. Any object that we recognize as such and possibly name is an invariant in a production diagram, or an invariant in a system way of interaction with its environment. The slide shows the scientific production diagram, a schematic representation of how objects emerge in the scientific system. At the right side of the diagram, we have experimental means and methods that usually correspond in a statistical model to entities in the sample space. At the bottom, we have operations related to the technological implementation of experiments, data acquisition, and statistical modeling. The theoretical side of the diagram at the left corresponds to the interpretation of statistical models and mathematical formalization of theories. In a statistical model, theoretical quantities are usually associated with parameters. At the top of the diagram, we have metaphysics, that is, the formulation of causal explanations for the phenomena under study that eventually lead to the formulation of new hypotheses. The endless cycling around this diagram is the typical modus operandi of science. Coherence in this process is manifested by the emergence of invariant objects or eigensolutions. As we studied in the previous slides, eigensolutions are characterized by distinctive essential properties, namely precision, stability, separation, and composition. Good objects, that is, true or objective ones, are those that comply with those essential properties. Moreover, good objects deserve to be rewarded, receiving a name, so that they can be represented in language. Eigensolutions, or invariant objects, or invariant quantities, are of course the key entities of a scientific discipline. But also empirical instruments and theoretical methods are all part of the scientific production cycle and must be represented in the pertinent specialized ontology. The illustrative figures include elements of circuit theory related to the construction of potentiometric pH meters. These theoretical and empirical instruments are of prime importance in the verification of chemical equilibria in reaction networks. What exactly do we mean by ontology? An ontology is a basis for communication. A scientific ontology is a controlled language, vocabulary, grammar, and semantics used to describe concept, means, and methods of a given discipline. The grammar or the language articulation rule must reflect the compositionality properties of the corresponding objects. Symbol grounding refers to our ability to effectively link symbolic, linguistic, or abstract entities to real objects. As we had already mentioned, the key entities in an ontology correspond to eigensolutions. It follows from the essential properties of eigensolutions that, in a statistical model, they are represented as a precise or sharp hypothesis. Moreover, there are statistical significance measures specially designed to access the quality, the truthfulness, the objectivity of this kind of hypothesis. Our favorite example is the E-value, the Bayesian epistemic value of sharp hypothesis H, given the evidence in the observed data X. The E-value has been developed by the Bayesian research group of the Institute of Mathematics and Statistics of the University of São Paulo. This research program includes statistical theory, logical properties, computational methods, and applications of statistical models based on the E-value. This research program also includes the development of an appropriate epistemological framework for the E-value. We should bear in mind that all other standard statistical significance measures were developed hand in hand with an epistemological framework, like p-values and Popperian falsificationism, and Bayes factors and decision theory. The main objective of this presentation was to build a bridge between two distinct epistemological frameworks: Founderentism, as developed by Susan Haack, and Cognitive Constructivism, as developed by the Bayesian research group of the University of São Paulo. I believe that both epistemological frameworks have much in common, and that comparative studies can be mutually beneficial. The illustrative figure in this slide shows the bridge Hercílio Luz, linking the city of Florianópolis to the mainland of Santa Catarina. I take this opportunity to thank the organizers of the 9th Principia International Symposium and the support received from USP, FAPESP, CNPq and from Universidade Federal de Santa Catarina.